Let's look at the two main types of energy that we'll encounter, and those include kinetic energy and potential energy. In short, kinetic energy is the energy of motion, and potential energy is stored energy. An object with potential energy will have the potential for motion. So, energy. Kinetic energy, as I said, is the energy of motion, and something that you need to know is that the kinetic energy is proportional to the mass of the object, and it's proportional to the velocity squared, or the speed squared. This is called a quadratic relationship. K is proportional to v squared. It's a linear or excuse me, it's a direct quadratic relationship. Direct in the sense that if v goes up, k goes up, and quadratic in the sense that if v goes up, k goes up a lot more. So in fact, if I make a plot of k versus v, it's going to look like this. As v increases, k will increase, but it will increase more and more as v becomes bigger and bigger. So if you imagine here, what happens if I double v? Well, that means that the kinetic energy will quadruple. Or if I triple v, kinetic energy is increased by a factor of 9. Quadruple v, 16, on and on. So that is a direct quadratic relationship. If you do work on an object, the energy changes. We just talked about that. So I'll just write it here. It's called the work energy theorem. Work is equal to delta E, but usually when we're talking about, we'll say that the work changes the kinetic energy. Though, of course, you can do work on an object and change its potential energy. The work, or the units of work and energy are the same. Usually in physics books, they'll use the Newton meter for the unit of work. Because remember, work is equal to the force, which is in newtons, and the displacement, which is in meters. So work has units of Newton meters. And then usually energy is in units of joules. 1 joule, which is abbreviated as a capital J because it's a person's name, is equivalent to 1 Newton meter. I prefer to use the joule for all of these because work and energy do have the same units. They are indeed the same. And also, we've already seen the Newton meter before. I'm not sure if you remember, but the Newton meter was a unit for torque. And torque is unrelated to work, or it's not related in this way, actually. So it's not the same as the unit for work. So I prefer to use the joule for energy and work, but you might see both. Now, also, the next type of energy, which is potential energy, is stored energy or work. Uh, let's just sort of be clear about our variables here, because sometimes students get confused. It's just sort of got to keep these straight in your head. Remember, the W is for work, K is for kinetic energy, if you prefer, you can write it as KE. In fact, in my other class, that's what we use. We use KE. Students tend to think that's easier, but your book uses a K for kinetic energy, and U is the letter for potential energy. I think that somebody chose U at some point just because of the great number of the letters U in this phrase, potential energy, but I'm not certain about that. Anyway, so U is the letter for potential energy, or you might see this as a less or more obscure term or less obvious term, PE for potential energy. I'm not sure where the heck they came up with that. Anyway, those are our variables. Potential energy is still going to be in joules, just like for work and kinetic energy. And there are many different types of potential energy. You can have elastic potential energy. Like if I have a rubber band, I'm going to pop somebody with it. If I extend the length of the rubber band, stretch it out, it has the potential for motion. If I let it go, it's going to move. I can have gravitational energy. We'll talk about all of these. That is, if I lift something up from the surface of the earth, if I let it go, it's going to move. It has the potential for motion. Also have chemical energy. We'll talk about this when we get into food and how we measure that. Nuclear, hey, we have a whole chapter on nuclear energy. An electric potential energy. We have a whole chapter on electricity too, which is a really wonderful chapter. I think you'll really like it. Now, you move an object of mass m to a height h. What work has been done on that object? Well, I have this mass m, and I apply a force to it in order to move it through a distance h. Now, my displacement, remember, work is force times distance, and in this case, the distance is h, right? I'm moving it through that distance h. But what is my force? Well, the force has to be at least the weight of the object in order to have a constant velocity moving this object through space. I have to have the weight. So the work done by this force is the mass times the acceleration due to gravity times h. Now, this work done has changed the energy of the object. And what it does is it gives it potential energy. So this work, which is positive, right? Remember we said that work changes the energy of an object? This work is converted then into potential energy. What we've just done is we've derived the expression for gravitational potential energy, that U is equal to m times g times h. So when I have an object that's above the Earth's surface, and we'll take the Earth's surface to be h equals 0. So wherever you're standing, the floor, we will assume to be h equals 0. Now, just a little aside, doesn't have to be h equals 0. You can really set that to be anything you want. But for the purpose of this class, we'll always have the ground to be equal to h equals 0. So if I move some object at some height h, it now has gravitational potential energy because I've done work on that object to lift it through the Earth's pull due to gravity. H here refers to the distance from some reference point, the ground, to the height. And that's what I was just saying, that our reference point, just for the sake of, making it easier, I'm all about making it easier, is that we'll always assume that the ground is h equals 0. Though if you're preparing for some other standardized test or some other class where you encounter potential energy, you should know that that doesn't have to be the case, that I can really let the top of the table be h equals 0. Or I can let some area below the surface of the ground be h equals 0. It's really just a reference point for us to figure out what is the object's change in potential energy. Now, if I have this object that has potential energy and it's some height above the ground, when you drop the object, the potential energy is converted into kinetic energy. And so we can do a simple little calculation here where if this U is all converted into K, then whatever gravitational potential energy it has is now converted into kinetic energy. And so, you might say, well, this seems like a really simple way to figure out the speed of something when it drops through a certain height. If I can really say that the potential energy is equal to the kinetic energy, then look, all I need to know is the h, the height of the object, the mass, and then I can solve for the speed of the object when it falls through that distance. And you would be right. It is a really simple way to figure out the velocity of an object or the speed of an object when it falls through a certain distance.